Abnormal molar masses. Why abnormal molar masses? Because of dissociation or association of compounds in some solvents. The reason is dissociation or association. Suppose we say molecule of NaCl and we dissolve it into water. You remember we have talked about a depression in freezing point, elevation in boiling point, all those things we have talked about if we add some solute. Till now, if you remember, we had talked that the solute is non-ionic, means it does not get ionized, and non-volatile. It does not get vaporized, for example, camphor, etc. We didn't talk about those. So ionization was not there. And also, we did not mention that specifically, but also the solute should not associate, means association should not be taking place, means two molecules should not combine with each other. Because if it happens, then abnormal molar mass comes into picture. So that's why we are giving the example of sodium chloride. Sodium chloride ionizes in sodium ion and chlorine ion. Yes, Varsha, all the assignments, magical series assignments are related to this chapter. What I have enabled and what I am talking about, those are related to this chapter, solutions chapter. Molecules of ethanoic acid, that is acetic acid, these associate. Dimerize means two molecules combined together. Di means two. So two molecules combined together. So effectively, it is one molecule only. For colligative properties perspective, it is just one molecule. So try to understand why I'm saying it. I said colligative properties are those properties which depend on number of molecules, not nature of molecules, or number of particles, not nature of particles. So if something gets ionized, means and NaCl gets ionized almost 100%. So if you have 100 molecules of NaCl, you will actually have 200 particles after ionization. So your molar mass calculations were on the basis of you have only 100 particles. But in reality, there are 200 particles. And colligative properties depend on the number of particles, not the nature. It means, in this case, colligative properties means boiling point, freezing point, these will change. Okay. Relative vapor pressure, this will change. Osmotic pressure, this will change. Similarly, in case of association also, for example, dimerization of acetic acid. This will also depend on the degree of dissociation or degree of association. I gave you example of NaCl because it ionizes 100%. So 100 will result in 200, 200 will result in 400, like that. Okay. But if it is not 100% ionization, then 100 will not result in 200. So if you have 100 molecules, these may result in 150. If this is just, the part of it part of it ionizes, okay? Not 100% in that case. Similarly, in case of acetic acid, two molecules combine and produce one. But if each two molecules combine and produce one, then obviously if you have 100, these will get converted to 50. But if it is not 100% association, then 100 might result in 80 only, because only few dimerized, not all. So that's why we need to consider percentage dissociation and percentage association here in this case. So when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. And I'll explain why. First, understand these 2 points, that during dissociation, The experimentally determined molar mass means actual molar mass is lower than the true value. True value means theoretical value. When there is association of ions, the experimentally determined molar mass is more than true value. Experimentally. Because, and true value is what? True value is before association or dissociation. True value when we are not considering ionization or dimerization, like that. Now, to understand this one, you need to understand by formula. The molar mass is given by this formula. In case of dissociation, number of particles will increase. And try to understand it because it is not given in the book, but is important for competitive examination. Questions are asked from this fact. Because number of particles increased means colligative property is increased. Means delta T is equal to Km. I'm not writing delta Tf or Kf. I'm saying in general, if it is for freezing, it will be delta Tf and Kf. If it is boiling, it will be delta Tb, Kb. And molality will depend on the number of moles, means number of moles increased. Number of moles means number of particles. So if initially there were 6.022 into 10 power 23 molecules, system will consider this as particle because it depends on number of particles, whether it is molecule, whether it is atom, whether it is ion, nature does not matter. After ionization, say it becomes 9.033 into 10 to the power 23 ions, total ions, some molecules ionized. And you know, molality is number of moles of the solute divided by mass of solvent in kg. Now, mass of solvent in kg did not change. It is same. It did not change. But number of moles of solute means greater number of particles, greater number of moles. 1.5 moles now instead of 1 mole. Initially, it was 1 mole. Means molality increased. On dissociation, number of particles increased, which resulted in molality increased. Now, if molality increased, delta TF increased or delta TB. If delta T increases, molar mass will go down as per this formula. Because none of the other things are changing. Kf for water, for example, solvent is water. Kf will be same, 1.86. Mass of solvent is not changing. Mass of solute is not changing. Only delta TF changing. Okay. So this is the reason that in case of dissociation, the experimentally determined molar mass is lower than the true value, and in association, delta TF will decrease, molar mass will go up. Therefore, what I am explaining, I am saying, and try to understand what I am saying. NaCl, Na plus plus Cl minus. I am explaining it for association. For dissociation, it will be opposite. Suppose in some part of it dissociated, some part of it ionized, not all. So initially say it was 6.022 into 10 to the power 23. Then after dissociation, there will be some NaCl. It will be 6.022 into 10 power minus, sorry, 10 power 22 minus X, some part dissociated, okay? And it will be X and X because the ratio is 1:1:1. So whatever dissociated, the same amount of sodium ion and chloride ion will be produced. And say the sum of these all particles is 9.033 into 10 to the power 22. I'm just giving an example. Now there is greater number of particles total, greater number of particles. So greater number of particles will give you greater number of moles. Okay, moles increase. Why? Because 1 mole is 6.022 into 10 power 23. So this will be 1.5 mole, it means moles increased. When moles increased, molality increased, because in the formula of molality, moles is in the numerator, moles divided by mass of solvent in kg. Molality increased means delta TF increased if it is delta TF. If delta TF increased, M2 decreased as per this formula. These are inversely proportional. Delta TF is in denominator. If it increases, it will decrease the value of M2. Is that clear? Okay. Underlying concept you need to understand. Okay. In case of association, it will be opposite of this one. Delta TF will decrease, M2 will increase. Now, molar mass that is either lower or higher than the expected or normal value is called abnormal molar mass. Why it is abnormal? Due to association or dissociation. It is abnormal. Normal value or true value is when there is no association or dissociation. Van 't Hoff introduced a factor I for this one. Van 't Hoff was a scientist. He introduced a factor I known as Van 't Hoff factor to account for the extent of dissociation or association. How much dissociation means ionization has taken place, or how much association, for example, dimerization has taken place. This factor I is defined as normal molar mass divided by abnormal molar mass. There are these three formulas used. Mostly you will be using these two, this one and this one. This one you will be using when in the question itself it is given like observed colligative property and calculated colligative property, then you will be using this. So first task for you before I move forward to write and memorize these. Van 't Hoff factor I is given by normal molar mass divided by abnormal molar mass, and then I'll talk about where we will be using it. So write it, memorize it right now. So I hope you have memorized normal, abnormal, observed, calculated, total number of before, sorry, after and before. The last one we will be using in one of the numericals. Although when these type of numericals are solved, either if we talk about NCRT or any guide, they don't actually say that we are using this formula, and they use it and students are confused there. We are actually using this formula in those numericals. So modified formulae are given by as per Van 't Hoff factor, and these formulas we already know. These formulae. P naught minus P1 means relative lowering in vapor pressure. P1 naught minus P1 divided by P1 naught was N2 minus N1 when we neglected N2, okay, as compared to N1. So N2 is much less than N1. Then N2 by N1. Otherwise, it was N2 divided by N1 plus N2. We introduced want of factor here, I. Similarly, in TB, delta TB equals to KBM, we introduced want of factor I. Delta TF equals to KFM I. Osmotic pressure pi equals to N2R RT by V. It was pi was CRT. C is concentration molarity, that is N2 by V RT. It was like this. But now with want of factor, it is I N2 RT by V. So in all cases, you will just multiply the right hand side by Van 't Hoff factor. I. Okay. And what is I? As per third formula, I is number of particles after association or dissociation divided by number of particles before association or dissociation. Now the question to understand this concept. 2 grams of benzoic acid dissolved in 25 grams of benzene. Benzene is solvent. 2 grams benzoic acid is solute. So W2 is 2 grams, W1 is 25 grams, and shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant Kf for benzene is 4.9 Kelvin kg per mole. What is the percentage association of acid if it forms dimer in solution? Read the question again before I start explaining. What is given? W2, W1, delta TF, KF given. Okay. And you also know a few more points which I'll explain during explanation. Okay, which I'll tell you. You have been asked the percentage association if acid if it forms dimer. Okay. Now, if it forms dimer, it will be the equation will be like this: two molecules of the benzoic acid will form one C6H5COOH whole twice. One molecule. Two molecules, one molecule after dimerization. Okay. So this will be the type of reaction here in this case. But according to question, not all molecules dimerize. It means that's why it is asked percentage association. Yes, Shivangi, association is taking place, Shashwat. Yes. So if initially, and understand it clearly, very clearly, this concept is very important. If initially, and this is something you have used in 7th grade equilibrium, sorry, 11th grade, 7th chapter equilibrium. So if it is initially 1 mole, initially here we had 0 moles of the dimer. But suppose in one, X is dimerized, X part is dimerized. So what is the ratio? Two molecules produce one molecule. two molecules dimerize to produce one molecule. It means X, when it is used, it will produce half of it, X by 2. Up to here, it should be very clear. Okay. Here you have two molecules, they produce one molecule. So if X is used, that's why I have written 1 minus X remaining. If X is used, X will produce X by 2 molecules. No, Shashwat. I'm coming to that. Okay, that's what I'm explaining. How to get the value of I. Okay? So initially, you had total number of moles or molecules. You know what is the molecular ratio? That will be same as moles ratio, because one mole is equal to 6.022 into 10 power 23 molecules. So it is just a constant. So in division, both will be cancelled out. 6.022 into 10 power 23 will get cancelled out. So whether you have the ratio of moles or you have ratio of particles, it will be same. So how many moles you have? 1 plus 0, 1. And after dissociation, how many moles you have? 1 minus X plus X by 2. 1 minus X left of benzoic acid and X by 2 produced of dimer, means 1 minus X by 2. So before you had 1, after you have 1 minus X by 2, and by the formula, third formula, I is equal to number of moles of particles after number of moles of particle before, means after divided by before. So here after divided by before, I will be after divided by before, that is I will be 1 minus X by 2. Up to here, is it clear or not? It should be clear before I move forward. Fine, good. So we calculated the value of I from the formula. How many moles are there total of all particles, including reactants and products, all after the reaction, and how many particles were there before the reaction? So when we calculated that, I think there was something else also to be calculated. Anyway, we will have to calculate that molar mass. Okay. So first we calculated in this case the value of I. And what is asked? What is the percentage association? So value of X is asked. Okay. But if we see from this formula, I is also given as normal molar mass divided by abnormal molar mass. And normal molar mass we can calculate by the formula itself. The formula is C6H5COOH. From here, normal molar mass can be calculated. What is the abnormal molar mass? Coming to that, M2 is equal to Kf into 1000 into W2. Here M2, I am talking about just not by this formula. Okay, 4.9 is Kf given, 1002 grams is given the solute, 25 is given the solvent, 1.62 is the depression and freezing point. Now from these we calculated M2 equals to 241.98 gram per mole. Now who will tell me whether it is normal molar mass or it is abnormal molar mass? Who will tell me whether it is normal molar mass or abnormal molar mass? So thus experimental value, this is the experimental value. Benzoic acid is this much experimental. Now we calculated the value of I. This is something I have explained. And we equated both. This is what value we calculated, and this is as per first formula, normal molar mass divided by abnormal molar mass. Normal molar mass will be as per the formula. This is the formula. This will give you normal molar mass. C6H5COOH. So if you calculate C6H5COOH, it will be 12 6 are 72 plus 5 plus 12 plus 32 plus 1. Okay. 7, 9, 11, 12. So 122 you will get, right? So the only unknown now is X. And remember, X is not percentage dissociation. X is just dissociation. So get the value of X from here. And once you get the value F, you can multiply this by 100 to get the percentage dissociation, because in the question, percentage dissociation was asked. Okay. Just I'm explaining it again. Percentage association in this case, not dissociation. Okay. Just explaining it again. Question says that benzoic acid, when dissolved in benzene, dimerizes, but not all. Some part of it dimerizes. Okay. With the equation, we will calculate the value of I in terms of X, because we will assume whatever is asked, percentage association is asked. Okay, so we will say let X part associated, X part of it associated, X by 2 will be produced, half of it will be produced. So if X consumed, X by 2 is produced. So overall after will be 1 minus X by 2, before was 1. From here we got the value of Van 't Hoff factor in terms of X. But we can calculate I, actual value of I, from the formula I equals to normal molar mass divided by abnormal molar mass. Normal molar mass is what you calculate as per the formula. This is normal. Formula of the compound here. But the equation for the M2, that formula that gives you the molar mass, will give you abnormal molar mass. Why that will give you abnormal molar mass? That will give you abnormal molar mass, this formula, because this delta TF actually depends on molality, which we are using here, depends on molality, and molality depends on number of particles. Now number of particles are different, actual particles. The number of particles different, molality will be different, delta TF will be different in this case. So whatever delta TF is given is for abnormal molar mass, not normal. So from this formula, you will always get abnormal molar mass in case there is association or dissociation. Otherwise, this will be normal molar mass. Equate both the values of I. So I we got 1 minus X by 2, and I we have normal molar mass divided by abnormal molar mass. We equated both of these values of I and got the answer. If there is any confusion, any step was not clear, let me know. Good. Um, yes, Vanna, that was approximately 242, correct? Next question. We will be using similar concepts. 0.6 milliliter of acetic acid having density 1.06 gram per ml is dissolved in 1 liter of water. Now it is given as water. And for water, you should know Kf 1.86 kilo kg per mole. The depression in freezing point observed for this strength acid was 0.0205 degrees Celsius. So delta TF is given. Calculate the Van Hoff factor and the dissociation constant of the acid. So in this case, it is dissociation. And you can calculate the mass because volume is given, density is given. Okay. So slightly different, it will be number of moles of acetic acid will be given mass upon molar mass. Given mass you will calculate because density is given. Mass will be volume multiplied by density because density is mass over volume. Mass, that is W2, will be density into volume, that is 1.06 into 0.6 grams. It will be in grams and we need in grams in this case. Okay? So number of moles will be this, we have calculated given mass upon molar mass of acetic acid. So we got number of moles. Mass of solvent is given 1 liter. 1 liter we converted to grams because water's density is 1 gram per ml. So we multiplied it by 1000 grams means 1 kg. Molality will be number of moles divided by volume, sorry, mass of solvent in kg. So we got the molality here. Now if we know the molality, delta TF is equal to Kf into M. We got 1.86 Kelvin kg per mole into the molality 0.0197. Direct formula based question here up to here. Okay, it is direct formula based question up to here. Then Van Hoff factor will be observed freezing point divided by calculated freezing point. Now this is formula 2. Most of the times you will be using first and third formula, but it does not mean that you will not be using second formula. It is the observed freezing point divided by calculated freezing point. Now in the calculation we have done so far, did we use I here? No. So tell me whether it is observed or calculated. Depression in freezing point. Calculated because observed will be when you have association or dissociation after that. This is calculation based on without considering Van Hoff factor, without considering association or dissociation. So here we calculated delta TF 0.0195 and 0.0205 is given in the question that after dissociation, this much was the change. Okay, so depression in freezing point observed for this strength acid was, so delta TF observed is 0.0205. Okay. So we used now these two values to get the Van Hoff factor. So Van Hoff factor calculated. Next is calculate the dissociation constant of acid. Remember, it is dissociation constant is asked. It is not dissociation or percentage dissociation. And here students make mistakes. Dissociation constant is asked, not dissociation or percentage dissociation. So for that, you will write how acetic acid ionizes. In previous question, it was association. So we use that equation. Here, ionization, so ionization equation. Initially, we say that we have N moles. So it is slightly shifted. Actually, it is N00. Then it will be N minus NX, NX, NX. Okay. Ratio is 1:1:1. So 1 mole of acetic acid if dissociates, then it will give you 1 mole of H plus and 1 mole of acetate ion. So if NX is used, NX will be produced, NX will be produced. Same ratio, 1 is to 1 is to 1. So total number of moles we can calculate by adding these after. After it will be sum of these. And from here we can calculate value of I after divided by before, N. So whether you consider N or you don't consider N, value of I will be same 1 plus X. You could have considered it like this also. CH3COOH gives you H plus CH3COO minus. Initially you say this is 1 mole and these were 0. And finally or after 1 minus X, X, X. Okay. If X dissociates out of 1, X will be produced, X will be produced because the ratio is 1 is to 1 is to 1. 1 is not written here. So 1, 1, 1. So if you add these, you will get 1. If you add all these, you will get 1 plus X. I will be after. After is 1 plus X. Before is 1. You will get 1 plus X. Same. Okay. And this value we have already calculated in previous part 1.41. So from here we will calculate X. Okay. So X we got 0.041. This is degree of dissociation, but we have been asked dissociation constant. Okay. So for dissociation constant, we need dissociation constant Ka will be concentration of H, concentration of acetate ion divided by concentration of CH3COO. So that's why we are now calculating the concentration of CH3COH will be N 1 minus X. Okay. Now N we have used 0.0106. This one 0.0106. So we use that value. And here why we used N, you can get value of I even if you don't use N, but we need actual value of N because we are calculating equilibrium constant. Here dissociation constant is nothing but equilibrium constant or acid constant here, equilibrium constant of the acid. So N1 minus X, substitute all the values, you found the concentration of acid. Similarly, acetate ion concentration at equilibrium is Nx, and same will be the concentration of hydrogen ion. Substitute these values in the formula and you will get the answer as 1.86 into 10 power minus 5.